Well, hello. Let's see. Last time we have figured out how to uh, come up with Shannon's entropy, which is supposed to describe the uh, amount that is of information that is missing in a given probability distribution. Now, the way that works, let's do our full screen here, is that, or the serious limitation of that approach was that it works for discrete distributions. If you have n alternatives, the probability pi of each one of them will give you a Shannon entropy given by this formula. And this entropy here is bounded between a minimum value of 0, which is what happens when you're certain one of these guys, in which case the probability is 1 and the log of 1 is 0. And the other ones, everybody has a 0 in front, so everybody is 0. So when you have full certainty, you get a 0. And when you are maximally uncertain, maximal amount of missing information, the probability is that of the uniform distribution, 1 over n. And you get something like that. Very good. So what I want to do today is generalize this to continuous distributions. And the purpose of the whole lecture, or at least this first half of the lecture, is to actually show that this is a problem. In fact, it is a problem with the whole interpretation of entropy being an amount of missing information. And the way they work this is, the way it sort of works is like this. Suppose that you say, okay, how do we generalize this to the continuum? Let me do it wrong. I'm going to say S, oh here, I'm not even going to write an equality. I'm going to say consider the following. Minus the integral of the x px log px. It seems that it's a natural generalization of this. In fact, it is the expression that we saw Gibbs used, where x would stand for the volume element in phase space. And so this is, and P would stand for the probability distribution. Okay. First remark to be made here, let's see, questions of notation. So our goal is going to be figure out, does this work? When does it work? What are we doing? Notation. By the x, what we mean is the nx, some number here. It could be v3, nx, whatever. So the notation is supposed to imply some d dimensions. X, it could be one dimension. Think of it as one dimension. It's fine. The problem arises already in one dimension. But this also includes, and it could include variables that are not just single dimensional. The other thing is that what we have here is a probability density. The probability that the quantity x lies contained between the value x and x plus the x is equal to a density dx, or the probability that the quantity x, maybe a vector, is contained within a certain region of volume, let's call it ddx. This is what we call px ddx. Things like that. So this is general, okay? It's a probability that whatever your random or unknown variable is lies within a certain range. So you have a probability density there. Now, what is the problem with such an expression? Well, let us try to, we have a pretty decent idea of where this one came from, the Shannon entropy. It came from obeying certain axioms, certain desirable features that we would like an amount of missing information to satisfy. Namely, whatever this amount of missing information is, it is a function of the probabilities. Second, whatever this function is, if you have a uniform distribution, then it should increase with the number of alternatives, the number of possible microstates. And finally, there was this interesting grouping property. If you're going to supply the information all at once, it is the same as if you supply it in one installment to fix within a certain group of microstates, and then try to figure out what happens with information when you're trying to figure out what happens within one of the groups, which is the true alternative with one of the groups. And the final result was that entropy. So let us go back to this expression here. To figure out what form of entropy we're going to use for a continuous distribution, it's a good idea to just say, let the probability pi be the probability density at the point xi, and then multiply by whatever that volume is. Maybe I should use a capital delta just to make sure that what I'm doing is I have this space, I have a probability density, like here. I'm going to discretize it into cells I, and so each cell I has a certain amount of probability, and so this is the probability of a cell I at the position xi. And so now we can definitely go and write, therefore, the probability is going to be the sum of the pi log pi, which is equal to, in this discretized version, p xi delta xi, that's probability of being in the cell denoted by delta x in the ith cell, and then log p xi delta x. Nothing wrong here. This is perfectly legit. Let's see what happens here when we try to figure out what this delta x is. So, for example, if we have in one dimension, if you have, here is the probability density, and here is x, and we discretize this. So you have a certain probability distribution, and you figure out that the probability of being in this cell is going to be, well, suppose that we're going from some minimum value to some maximum value, and then the probability, we can write the delta x, well, let's write the xi as being xa plus a certain number I of delta x's. So this is an integer. I should have called it n. In the lecture notes, I have it written as n. So the probability pxi dxi is going to be whatever pxi is, and then the delta x is just going to be the difference between the highest value and the lowest value, and let us assume that we discretize it into n intervals, equal intervals, n equal intervals. So this is delta x for n equal intervals. Then the entropy is minus the sum pxi dxi. Let's just keep writing this dx like that, and then I'm going to write the log in two pieces. I'm going to write the log of pxi delta x. Delta x is going to be xb minus xa. I'm going to write it like this. 1 over xb minus xa. That's this piece. And then all divided by n. So there is a 1 over n plus log 1 over n, which is the same as minus log n. Let's proceed further. S is equal to, okay, here we go. Now, when we're doing this, we're going to call this guy here, let's look at, what do we look at first? Let's look at the P, this is the PI log n, there is a minus and a minus, this is a plus, log n, and when we do the sum over all of these px's, of course, this adds up to 1. So we get log pn for the second piece. And then we have minus. And when we take the limit in which the delta x goes to 0, when n goes to infinity, there is no problem with this guy, no problem with that one, there is absolutely no problem. That's the definition of what a Riemann integral is. So this is the x px log px divided by 1 over xb minus xa. And that's what it is. Now you see what the problem is here. When we try to write the discrete entropy, right? This discrete entropy here, and we try to write it for a continuous distribution, we can get pretty close to what we have back here, except that, well, okay, we have this extra piece here that's not problematic at all. I mean, we could even have included it like way over there, but we have here a problem. This entropy here, the entropy that we wrote up here, is the one in which we have discretized with n intervals. So let me write Sn, and let's be a little bit more explicit. And so if we have here Sn, what we have there is that for large n, Sn looks like this. And so the problem is the limit n goes to infinity does not exist. So in principle, you cannot write a Shannon entropy for a continuous distribution. Now, is this unexpected? Is this a surprise? Well, in a sense, it's not. Remember the second axiom of Shannon, when he said, when you have a uniform distribution, the entropy is going to be a function of the total number of microstates, the total number of alternatives. If the number of alternatives, and that function was an increasing number of n. So if the number n increases, you're going to keep on increasing. There is no limit, right? So the fact that you're going to run into this kind of problem was already implicit in Shannon's axioms. Let's continue. We can actually say it differently. If in order to pinpoint one alternative in a set of several, you have to provide some information. When you have more alternatives, you have to provide more information, right? And if you're going to go all the way to the continuum, you're going to have to provide an infinite amount of information. To figure out an integer among a set of 5 requires a certain finite amount of information. If you want to describe a point in a straight line, that requires an infinite number of digits, an infinite amount of information. So you see that the problem was already at the level of formulating the Shannon axioms. And so how can we bypass this problem? Because if the only entropies you can write are for discrete variables, then the whole thing doesn't it's not useful. It just doesn't work. It's not general enough. We need to do it for continuous variables. So let us try to see how we can fix it. Perhaps one way to fix it is to get this guy, the log n, which is the culprit, and get it onto the other side and explain that S, the entropy of a continuous probability distribution, is going to be obtained as the limit as n goes to infinity of Sn minus the log of n. Well, if you do that, you see that, well, yes, Sn tends to diverge with the log of n. If you get the log to the other side, there is no problem. It's finite. So that works. But please notice that the interpretation of as the amount of missing information is already gone. All right. So that once again tells us it's the same problem. Maybe your interpretation is not quite correct. Very good. So that's one possibility. Let's continue. So then we're going to consider the following. Consider the following integral from xa to xb, an integral of a density, and then log px, just like that. Let's continue. Let's go back to that. Whether we divide this px by the constant 1 over xa minus xp minus xa or not, we'll discuss in a second. We'll come back to that. So let's go back to this one now. What happens when you change variables? Suppose you change variables. Suppose you change variables to from x to a variable y, which is some function of the x. Then the probability px changes into a new probability distribution, which is now a function of y. And of course, the change is such that if you figure out the probability within a certain region, a small region, a small little volume, this of course is the same as the probability of y within the corresponding volume. All right? The idea I have in mind here is the following. Imagine that you have a flat plane described in Cartesian coordinates. This y is not that y, right? This is just Cartesian coordinates. Or we can also describe it in terms of polar coordinates. Then it should be fairly clear that when you describe it in Cartesian coordinates, this should be the same as the description in terms of the polar coordinates, and here we have dr d theta, right? That just means you're changing coordinates. The probability of being in a particular little volume element here, where you describe it in terms of x, y, or r theta, it's exactly the same. And the particular formula that one uses in general is to say that whatever this is, it's equal to something like dy. And here we're going to rewrite this dy in terms of the x coordinates, and the appropriate change is through a Jacobian. And now you can go ahead and eliminate the dx's. And so here you have the connection between the new probability distribution and the old one. I'm sorry. Did I write this right? No. No. Let's do it right. I'm being lazy. dx. We want this to be py dy, but the px dx can be written as px dx dy Jacobian dy, and of course when you now compare those two, you find out that the new probability distribution is going to be the old multiplied by the Jacobian. Very good. So what's the problem with this probability distribution? Well, let's change variables. When we change variables, we have change variables xa to xb dx log px. This is going to be equal to, now these are the corresponding ya yb's. dx happens to be invariant, and so this is the guy that's just py dy. And then here we have log px, which we have down here, px. So this is going to be py divided by the Jacobian. So this is going to be py, and this is going to get divided by the Jacobian, which is the same as doing dx dy, like so. I inverted it. This is a determinant, so whether you write it down here as dy dx or here as dx dy, it flips. Very good. So now you see you have a problem, because which is the formula for entropy? Is it going to be this one, option 1, or option 2? Which is it going to be? If you decide that this is the correct version, then in the y variables, it's going to have a factor here. If you decide, on the other hand, that you just started with the y variables, why not choose this one? Which is it? That's the question. And that's a serious problem. If we go back, so what's the solution to this problem? The solution to this problem comes when you actually look at what we did when we discretized, and you saw that there was an extra piece here that just said, look, if you take the distance between from xa to xb, and you were to assign a uniform probability distribution between xa and xb, this object here is basically a uniform probability distribution. And by uniform, I mean constant in x. So going back to the discretization, the answer is we should write the entropy as minus dx px log px divided by a uniform probability distribution. And the problem, of course, is that the big thing here, the insight, is that whatever happens to be uniform in X is not going to be uniform in Y because there is this extra Jacobian floating around. So the idea here is that mu X is supposed to define what we mean by the uniform distribution. When we discretize, we're supposed to discretize in equal delta x's, but equal delta x's does not correspond to equal delta y's. Equal delta x's in Cartesian coordinates is not the same as equal volumes in Cartesian elements is not the same as equal volumes in polar or spherical coordinates. So which is the one that's supposed to be like truly uniform? This mu is what defines what we mean by uniform. Now, so we need to have a sense of what a volume is in this space. If you don't have that, you cannot do it. Once we have that, however, once we have that, then the problem is solved. The problem is solved because mu x dx, the probability in the little volume dx, is actually the same as the probability mu prime in the little volume. Let's write it as I was writing it before in the coordinates y. So that when we have the entropy being expressed in x's, we will write this in terms of y's now, and we have dx px is going to be dy p prime y. The log is going to be p prime dy, and here we're going to have the Jacobian, and the new distribution mu x will become mu prime y, and here we have the Jacobian, so that the Jacobians cancel out and we end up with exactly the same formula log py mu prime y. So this is the answer. Shannon's entropy only works for discrete variables. If you're going to apply all of this to continuous variables, then the formula properly should include dividing by a uniform distribution. What do you mean by uniform? And if you do that, then changing variables doesn't matter what this means is the uniform distribution described in terms of x gives the same probability to a certain volume. That's the uniform distribution described in terms of y. Even if there are Jacobians floating around, it's just a matter of saying equal volumes get equal probabilities. So let me re-express this in the following sense. Important piece of language. A uniform distribution what is a uniform distribution? Is such that it assigns equal probabilities to equal volumes. That's what uniform means. This does not mean the distribution is constant. The density is constant. Uniform and constant are not the same thing. So let me draw that, make that very clear now with the example of the spherical coordinates. If you have a probability distribution in Cartesian coordinates, x, y, z, and this is dx, dy, dz, then we're going to be able to write this as some kind of probability distribution. And now I'm going to change to spherical coordinates. This is going to be in spherical coordinates r squared sine theta d theta dr d theta d phi. All right, so this is a standard spherical coordinates. Now, whatever appears multiplying the dr, the infinitesimal, the dr d theta d phi, this is what we call the probability density for r theta phi. So in this case, we have a clear idea of what it is that the Jacobian is. The Jacobian is the factor here, r squared sine theta, that multiplies that. So the density in xyz is equal to, when multiplied by the Jacobian, is what gives you the density in r theta phi. So obviously, if this is uniform, if we have a uniform probability distribution, this is what you're going to get. The uniform is given like that. But being constant here means this guy is not constant. Why? Because there is the r squared and the sine theta. So constant and uniform are not the same thing. The definition of uniform is equal probabilities assigned to equal volumes. And the crucial fact to be remembered here is, what precisely do you mean by volume? You need this definition of volume. If you're dealing with a Euclidean space, 3 dimensions, then you have a pretty decent idea what the volume might be. Okay, just regular formulas for volume. But when your probabilities are, when you're dealing with spaces in which that are curved, is there a notion of volume there? There might be, there might not be. When you're talking about the probabilities of, say, positions, yeah, okay, there may be a notion of volume there. But you may be talking about the probability of a color. What is the volume in the space of colors? You don't have that. So what this is all telling us is that if you want to really define a notion of entropy in a space where the variables are continuous, you need to come up with a notion of volume in that space, something that tells you the uniform distribution will assign equal probability to equal volumes. So you see that notion of volume there is going to be important. A notion of geometry in the space is going to be very important. Very good. Here's an important remark as well. Notice that the formula that we have come out with for entropy is actually something like that. There is the log px log mu x. The formula that we have come up here happens to be the Kullback formula for relative entropy that we had seen before, where you have two probability distributions, the entropy of one probability distribution relative to another, and the another that we're talking about here happens to be the uniform version. So there is the moment that you want to make your entropys of continuous distribution, the formula that matters is the formula for relative entropy. Relative entropy is the fundamental quantity. The fundamental quantity is not entropy, it's relative entropy. Of course, we're going to drop this term eventually because it's very boring to have to say relative entropy all the time, and we're just going to call it the entropy. And say in the discrete case it becomes simpler. Maybe I should say it like this. We all know that energies are always relative to some origin of what we mean by zero energy. All energies are relative. You can adjust the zero of the potential, right? All energies are relative, but we do not go around saying relative energy. You just say energy, and we know that they're all relative. Same thing is going to happen with entropy. Entropies are going to be relative to some underlying measure of volume, but we'll just call them entropies. Very good. Notice also that if you start from note also that if you start from the discrete version, the discrete version of relative entropy, and so here we have the sum from I equals 1 to n of pi log pi mu I. Now we can play the same game. Start from relative entropy and write q p mu. We're going to write this as being the sum of pxi delta x log pxi delta x mu xi delta x when I goes all the way to n. So now we see that there is absolutely no problem here in taking the limit n goes to infinity, because this quantity here, which is the one that contained the 1 over n, disappears. They cancel out. And so as we do that, we obtain the appropriate formula but here we have a ratio of 2 densities. So the Jacobians cancel out, you can change variables, everything works. Perfect. So what is it that we are supposed to remember from this? The Shannon entropy, which is the one that we derived with the idea of having been interpreted as missing amount of information, only works for discrete variables. The moment you make them continuous, everything goes down the drain. And the reason is that if you're going to figure out the total amount to figure out one alternative among a discrete set, that's finite. But describing a point among a continuous of points, that requires an infinite amount of information. So infinites are a problem. Furthermore, you have to decide, if you're going to use the Shannon axioms, you have to decide what you mean by equal, an equal discretization, equal intervals, and equal intervals in x and equal intervals in changes of variables to y are not going to match. So you're always forced to come up with an idea here, what you mean by a uniform distribution. What we're going to do later, in some other few classes, is we're going to generalize the notion of entropy so that we never have to talk about amounts of missing information, and we're going to see that immediately the quantity that appears is going to be something like the relative entropy that we had here, where we have two probability distributions. This is going to be the relative entropy of S of P relative to mu, and mu need not be uniform. It can be whatever you want. So it's going to be of S of P relative to a Q of X. It's a generic formula. Very good. I think this is enough for now. What I want to do next is now, having appropriately criticized the notion of Shannon entropy as being a measure of amount of missing information, what I want to do is now do something constructive with it, and we're going to discuss the method of maximum entropy. That's for the next part of the class. See you then.